Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I want to talk to you about the oreChem project, and I'm going to give a rather high-level overview. I'm going to be more motivational than going into depth. You can read about it in depth, and I'll just give you the highlights of the thing. The project is a collaboration between a cast of thousands, UK participants, US participants, Australian participants, and of course Microsoft Research, which not only funds the project, but lends some intellectual energy to it. So with that, I want to start by talking about, by alluding back to the book that Tony Hay talked about yesterday morning, and that Herbert von de Sample and I have a chapter in. And what we talk about in that book is a quote that we've used quite a few times in talks, that the current scholarly communication system is nothing but a scanned copy of the paper system. And what we're talking about there is the fact that a lot of the stuff that's been done up to now in moving scholarly communication over to the web and to the internet is basically taking static trees and ink and turning them into static PDF. And that misses some of the opportunities that we think are really available here. And we point out three things that are happening that are very promising that lead us right into the ORE chemistry project, which is the notion of machine actionable substrate, the notion of the artifacts of scholarship being machine readable and therefore machine processable and therefore machine recombinable, the integration of data sets into the publication process. As you probably know, data is not something that is commonly published in the scholarly reward system, and the exposure of process, the ability to go back and look at the provenance of things and aspect of scholarship like that. So with saying that, that leads us into this sort of co-phenomenon that's happening right now with the changing nature of scholarship, is this Web 1.0 to Web 2.0 transition. And I won't say more about that. We certainly know enough about that. It's this going from a mostly read-only web with a lot of readers, but very few generators or producers, with a huge amount of producers and a very this notion of collective intelligence. And what we're trying to do in this project and other associated projects is to move scholarship into that domain. And there's certainly other people like Dave DeRoer have done a lot of work in that area. So this is generally referred to as Scholarship 2.0. And this is Tim O'Reilly's meme map changed by Carl Lugosi. Tim O'Reilly did the meme map of Web 2.0. And this notion of underlying concepts down below, open data, the long tail, open access, the right to remix, and things like that, which are then manifested in a whole bunch of really amazing things that are starting to happen, things like PLOS and open wetware and Zotero and a whole bunch of things related to scholarship, with this whole notion of scholars controlling their scholarly output and how it's used, rather than being controlled directly by publishers and given over to publishers. So the sort of the Semantic Web, Web 2.0, Tim Berners-Lee, et cetera, dream is this notion of the linked data cloud, of producing a substrate or infrastructure of data on which we can build new scholarly artifacts. And this is very much where we're trying to go in the ORE chemistry project, and you'll see the things we're doing there. So I want to make clear that scholarship is not just any web application. We make the mistake of thinking that you put up a web page and you throw your papers up there and suddenly you've done Scholarship 2.0 and you've moved your stuff over to the web. And there's some very specific requirements of scholarship that have to be fulfilled before you move it over to the web environment. And one of those is the notion of really expanding the notion of the document, which is moving from, this does not look like the slide I changed this morning. It is the slide I changed this morning. Anyway, it's really moving from the notion of just a text-only document with maybe figures and tables embedded in it, and producing this document, and I'll put that in big quotes, which combines data, images, and a whole bunch of other things. And what we tend to refer to this as complex or compound documents. And the ability to have a wrapper around these that makes them things that we can work with. That, clearly on the web we can combine things, we can link to things, but we don't, the combination, the groups of things are not are not things that have a first-class presence on the web. And this is where the ORE concept comes into this, and that's where I'm going next. So this is an example of an astrophysics paper that contains an X-ray observation, a bunch of data, data behind a graph, and these are not just dead objects, they're living objects that should be able to be reused. So if we're going to reaggregate and reuse those things, we have a couple of things that we need to be able to do. Blah, 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 transitions. Every time you put transitions in slides, you say to yourself, why did I do this? Because you always just click through them, I should learn. So you need to have an identity for these things, and you need to have a description. If they're going to be citable objects, one of the core notions of scholarship is the notion of citability and provenance and provability of where you got your sources. So if we're going to have the ability to form these compound documents which combine a bunch of things, those things must have an identity and they must have a description. We can't have these things which sort of change shape or change form or don't exist anymore if we're going to cite them in the manner that we cite scholarly papers. And similarly, if we're going to build these Web 2.0 social networks around these aggregations or these mashups, here goes another one of these transitions that I'm going to be sorry I've done, and really produce this notion of object-centered sociality where we allow collaboration, groups to form, presence, sharing, reputation, and relationships around these objects. Again, we need to have the notion of identity and description around them. These have got to be identifiable things. They just can't be fly-by-night ephemeral objects. So what came out of that is the work that Simeon Warner, who's in the room here with me, and myself, and Herbert von de Sample, and Michael Nelson, and Rob Sanderson, and Pete Johnston, got them all, did about, what was it, 2 years ago now, Simeon, right? On this Open Archives Initiative, Object Reuse and Exchange, with support from Microsoft and some other people, is to come up with a way of taking this web graph and saying, what I want to do is I want to put a circle around a bunch of objects, a subgraph, create an object which represents that subgraph, and then create an object that describes that subgraph. And so what we have is a first-class object on the web now. It's any web resource with the URI that is the thing that stands for this group of things, and then a thing that has a set of triples that describes that set of things. And now we now have the description of the boundary around this thing and the identity of the thing itself. And I won't go into the gory details, but it's very important that the URI of the description, which is this guy right over here, be distinct from the URI of the aggregation itself, which is distinct from the URI of the entities that are contained within it. So this is the essence of OAI ORE, and I encourage you, if you're interested in it, to look at the web page. This is the basic low-level data model, the notion of an aggregation with aggregated resources, the notions of a resource map, and how it's and things like that, and how it's produced. So that's OAI ORE, and that's why it's called oreChem, because what we're trying to do is now leverage this model and use it in the chemistry domain. So let me talk about oreChem in particular and tell you the things that we're working on, and I'll go into a little depth on these. The first one is this notion of at-source capture of experiment data in the research process. And Jeremy Frey's group and other people at Southampton are working on this notion along with others of electronic lab notebooks. This ability really to produce the triples at the source, to produce the data at the source. This notion of compound object authoring, this ability to be able to produce these compound objects as you're authoring the documents themselves. The notion of retrospective harvesting of chemistry data, and I'll talk a lot about that because that's where our current effort is. The notion of representation and reuse through common data models and ontologies, and therefore storage in a common triple store. And then lastly, the notion of the notion of this cloud-based triple store, where you actually store this stuff and make it available in the cloud. And lastly, the notion of chemical structure search. So I'm going to particularly touch on the retrospective capture in this talk, because that's the work we've done so far. So in the future ideal world, here we are, it's 20 years in the future and everything's perfect. The semantic web has come to fruition, even though we've been waiting for it for about 15 years now. Any day now, I see it. I saw it up. I was taking a walk today, and I saw it on the horizon. So this is a slide that I stole from Lee. And this, you showed this on Wednesday, I believe. This is work that Peter Murray Rust is doing with Microsoft in producing a plugin for Word to allow, whoa. Where did that come from?
University of Transylvania.
Produce a plugin for Word that allows authors to make chemistry compound documents with semantics built into them. And this is really, really interesting and important work because it allows authors to use a commonly used tool to produce these kind of documents that we're talking about here and have the data embedded in them or attached to them. And then in the other part of the ideal world, there we are, we'll have chemists working in the lab on very socially relevant and important experiments. And as they're working on that, the data will actually flow from there as they're running their experiments in the lab. I don't know the results of this experiment yet, but I hear they're not good. It had to be Mel Brooks, you know. So, but unfortunately, this future world, this perfect world, is not there yet. And in fact, the future world will never really exist because in chemistry in particular, legacy data is extremely important. Chemistry is a discipline in which legacy research results are as topical as current research results in many parts of chemistry. So what we're stuck with is, unfortunately, either physical pages or scanned reproductions of physical pages. But we have this, the data is then buried, oh, there we go, is buried inside of these things. We've got to figure out, and the descriptions of experiments and reactions are buried inside of there. So what we're doing in, by the way, that paper is supposed to be up in the corner over there. Yep. This projector makes things disappear, so we'll see what happens. So what we're doing is we're doing this retrospective conversion and pulling stuff out of those dead documents and making it live again. I believe you called it making cows out of hamburger. Yeah, Mark has a wonderful slide that he'll talk about of making cows out of hamburger. So we have the hamburger, which is the PDF document hiding up there. And the chain, you know, this chain is an idealized chain, but we start with Penn State, one of our partners that has a wonderful tool, part of its SEER suite called ChemXSEER, that they take that hamburger, and out of it they can pull out the bibliographic metadata, the citations. They can look at the figures and pull the data out of figures. They can look at the tables and pull the data out of tables. And they chunk the document. They say, here's an interesting thing that we might want to, that might refer to an experiment or might refer to a reaction. They then expose that through the oreData Model to our next partner, which is at Southampton, who consumes that stuff from them, takes stuff from eCrystals, and then magically looks at the NMR spectra and pulls out information from that. And Mark's going to talk about that later in this session. Mark does some, I'll say, he's going to be afraid to brag about his work. I know Mark, he's very humble, isn't he? But Mark does some absolutely fantastic work in finding these illustrations and pulling data out of them and pulling interesting stuff. And then at the same time, other people in the group are pulling out descriptions of experiments and actually fitting them into an experiment ontology. So they're taking text and they're pulling out what's been worked on, what was the process, and things like that. They then send it a short distance away to Cambridge, or they don't send it. They make it available again through this oreData Model. So they keep expanding. We have a set of triples here. We keep expanding the triples over here. And people at Cambridge, using sources like Crystalli, PubChem, and Wikipedia, then take that and interpret that more, and out of that pull reactions and molecular compounds. So they look at the text again and they figure out what reactions are being talked about and deconstruct them, and then they pick out what molecules are being talked about and link them to sources like Wikipedia, which is a really great source of, I forget the figure, there's a huge number of descriptions of common compounds and uncommon compounds. They then make that available again and pass on an enriched triple down to Indiana, who does some computational chemistry on them using Gaussian, pulls out more information, enriches the triples even more, and throws this all into our triple store in the cloud. And they're doing some interesting work there. And in the end, we have this fabulously enriched set of chemistry RDF triples that are then available for use by people to do all sorts of other applications. So we have this wonderful, come on, do it, there we go. There go those triples. Moving along the chain. I didn't spend all afternoon yesterday working on this for nothing. So, okay, so that's where we are. And this is great. I mean, look where we start. We start with this, with this dead stuff over here. And out of it, we get data. And, unfortunately, this is what we're going to have to do, and this is what other disciplines have to do, because this stuff is never going to be converted all the way. So this is cool stuff, and I'm responsible for very little of it, so I can say it's cool. It was Robert Walensky who said, I just do the PowerPoints. So this requires a significant amount of work on ontologies, and we're doing some interesting work there. We have 4 different ontologies they're working on. Nico Adams, who is at Cambridge, who's now at EBI, is working on a chemistry ontology called ChemAxiom, which is based on the basic formal ontology. And he's in the midst of doing some extremely interesting work in this area that I believe he's published at this point. It's called ChemAxiom. And then Mark and his colleagues at Southampton are working on an experiments ontology, which is based on this notion of distinguishing between experiment plans and experiment processes, which is really interesting stuff. This is actually what I'm responsible for, of working on the notion of a document ontology. How do you describe documents and their compound parts? And this is actually an extension of the oreData Model. The oreData Model talks about primitives of objects and their aggregated objects. In this, we refine the properties of OAI, ORE to talk about scholarly documents in particular. And then the last piece of work on ontologies is a reaction ontology, and this is coming out of, this is Cambridge. This is Cambridge's work of talking about reactions. So all of these fit together, and they all plug into that document ontologies, because you have documents that talk about molecules, that talk about reactions, and talk about experiments, and you can see how all that stuff goes together and fits into the triple store. And in the end, you have this wonderful world of a data substrate, a semantic graph that represents that substrate, and the ability to mash up and reuse this stuff. So where am I on time? 13. Oh, my God, I've gone too fast. Too many cups of coffee. Anybody have any questions while I'm taking my drink here? Yeah.
So how are you encouraging people to write their papers in a form that just directly fits into your model as opposed to having to do this extensive scanning?
Are you a chemist?
No.
Okay, so then we can speak I can say something that may speak. We can do mutual ignorance together, and we can pretend it's true, and the chemist can tell me I might be wrong. Chemistry has a very regularized writing style, according to my sources. The papers papers in chemistry are very different from papers in other disciplines. They're sometimes quite short. They have a large number of authors. They talk about the synthesis of a compound. There's a very regularized format, and the language is easily learnable. Did I get that right, the chemists in the room? Whew. Boy. Yeah. That was my next point. I mean, it's very important, and I'm going to talk about this in a second, that these things we call disciplines are broken up into many sub-disciplines that sometimes look very dissimilar. But specifically synthetic chemistries. And there are a few other aspects of that are that way. So that's mainly what we're working in at this point. Computational chemistry is a little bit different. Theoretical chemistry is different. But the methods that we're doing, and this is Lee Giles' work and Mark's work and work at Cambridge, really is something that can be extended to other disciplines, because there are regularized languages that are used across disciplines and can be tweaked. Other questions before I know I went way too fast because I thought of my flight.
I wasn't clear how much manual intervention is required to do the process of taking the dead paper and turning it into something into a set of triples.
I don't think, Mark will speak for his own work, which he's going to get to. Very little intervention. Yeah, he puts his. I think he drinks. I think he goes to the pub and he gets a pint. And
that's true for all of the
yes.
3 or 4 different stages.
Yeah, it's really quite remarkable work, and I recommend that I'm certainly willing to get email and send you on to the right people if you're interested in how this is done. Okay, so here's this again, our perfect world in which we have this wonderful semantic thing and everybody's cooperating. And everybody's behaving themselves. And, I've shown this slide before. We people who like to do technical stuff have to deal with these unfortunate things called people. And people don't always cooperate, and in fact, sometimes they're a little bit anxious to smash up our newfangled machine because they don't think it's the right thing to do. And chemistry is a particularly notable example of a scholarly area that is highly resistant to certain aspects of scholarly communication innovation. And one prominent example of that is how differently they behave to something that we all think is wonderful, like at least those people who are my friends. The physics archive that Simeon Warner is here and does a lot of work on. As you may know, the physics community did this thing in 1991, which worked out wonderfully and is essentially the communication mechanism for that whole high energy, a sector of chemistry. Yeah. Certain areas of chemistry. And as you move to other disciplines like biomedicine, you see something quite different with PubMed Central, in which the scholarly societies took control, and it was modified. And then an experiment with ePrints was taken with chemistry, with the chemistry preprint service, and it just crashed and burned. Didn't go anywhere. So these communities act very, very differently, even though they all look like scientists. And in this area, we've done quite a bit of work. Teresa Veldin, who's also on the project, who's a graduate student of mine, and I ran a workshop about a year ago in which we pulled together a whole bunch of chemists, information scientists, policymakers, publishers, and we talked about what is it that makes chemistry so interesting. And you can see I cut and paste. I took an image of a word here, so it's saying that I've misspelled myself. But we have an absolutely fantastic white paper, which Teresa mostly wrote. That's why I can say it's wonderful, that we're going to make available to the public in December, and we're going to introduce it with an article in Nature Chemistry in the December issue. So we have an article which is called Communicating Chemistry that's been accepted by Nature Chemistry and will contain the URL to the public version of the white paper. And if you're interested in this issue of this really socio-technical aspect of these problems, which I would argue is as important or more important than the technical aspect, I recommend you take a look at this. And
so, Carl, just as you invited questions a few minutes ago, do you explore in that anything of the observation that there isn't a physics industry, but there is a chemical industry?
Yeah, my next slide actually talks about that. I just here's a few of the highlights. I mean, I can brag about this again because Teresa, everybody should have a graduate student like Teresa. There should be millions of Teresas walking around because they're mature, they have good hygiene, and various things like that. Yeah, I'm not referring to any specific graduate students who are the opposite. So chemistry is particularly challenging because of the commercial value of chemical information. I mean, the pharma industry. I mean, chemists make money off of what they do. And as I think it was who said about astronomy data that no one makes lucky because no one makes money off it. It was either Bob Hanisch or Alex Zalay or somebody like that. What?
It was Alex Zalay. Nobody cares about it.
Yeah, nobody cares about it. And so. The next one is this notion of a very different research culture in parts of chemistry. It's the predominance of synthesis which overshadows discovery. Roald Hoffman, who was an attendee of the workshop, who is a Nobel Prize winner in chemistry, said that chemists view themselves as creators. Synthetic chemists are creators. They are fabricators. They produce things, and they just don't sit there and observe. They don't do stamp collecting, which is what the insulting remark they'll make about other sectors of the scientific world. There's a huge amount of autonomy. There's a lot of successful research is carried on with sometimes limited reliance on others. And the scholarly societies, qua publishers, have a huge monopoly. The ACS, is anybody from the ACS in the audience? Oh, good, because the last time there was somebody, and he caught me after and started to slap me around across the face. I was at Penn State giving an earlier talk on this, and he said, I don't like the things you said about the ACS.
They'll see you anyway.
Oh, my God. Wait, I'll put on my disguise. So the ACS, and if you don't know this, there's a wonderful identifier system in chemistry called the chemistry abstract. It's just the CAS number, which every single chemical compound has a CAS number, right? Well, wait, I'm going to say that wonderful in the fact that it works really well.
Actually, the answer to that is no. Registered chemicals have CAS numbers.
Okay.
There are millions of chemicals that are not registered.
Okay, registered, every registered chemical. Excuse me for saying that. There are undiscovered chemicals. Is that right? Okay, okay, but every registered chemical. Well, unfortunately, to use that number, you have to pay the ACS. So this is a great example of an identifier system owned by a monopoly, and that's a bit problematic. And the RSC has similar problems. I would argue not as bad. So it's a particularly challenging area. Simeon, I got to get to the airport. My daughter's waiting for me. Okay.
So you want me to create a distraction?
Yeah.
Carl, the good news is you've only got 5 minutes to dig the hole deeper.
So with my last slide, I'm an information scientist. I'm not a chemist. So the future is we have hopefully another year left in this project, and hopefully by December we're really going to get that process all in place and get this triple source start to build up and really start to demonstrate value-add applications that really make a difference to chemistry scholarship. We want to continue to understand these socio-technical barriers because we think it's essential to doing that in conjunction with the technical work. And we're hoping to get an international workshop or study funded as a result of the white paper and use chemistry really as a canary in the coal mine because there are other fields and there are other places that this thinking is totally appropriate. And then we're very excited to integrate this with a larger infrastructure effort. I am the Cornell PI on our DataNet. The NSF, through the Office of Cyber Infrastructure, is funding very large data conservation, preservation, and curation projects. And I'm the PI at Cornell with a project that's centered at Hopkins called Data Conservancy. And we're hoping to link these together and be chemistry be another leg in the disciplines that they're doing with that. So this is really interesting work. It's a bunch of really interesting people, and I encourage you to keep an eye on it. And I thank Microsoft for their support. Any closing questions? Yes?
So I was responsible for building ChemSpider.
Mm-hmm.
So I've only been here for the RSC since June.
Okay.
Some people are already calling ChemSpider the public registry.
Yeah, ChemSpider is great. I mean, that yeah.
RSC is not all that.
Yeah.
So we love to work with you on this because ChemSpider is intended as a free resource for the community. We're working on some of these efforts ourselves. Certainly we want to aggregate data and put it in there for other people to review.
Well, that's great. I mean, I'm sure you know my UK colleagues, Jeremy and Peter. So okay. Other questions? Well, I thank you for letting me go first and for sticking my foot in my mouth. It's always. But
Thank you.
Thank you.